Good morning. Let us start today's class. In last day we have seen that how to do the small signal analysis, and if early effect is considered, then we will have the R naught, otherwise we will be having the gain as minus GMRC that we have discussed. Now, let us quickly solve a problem so that we can understand what is the meaning. So, a problem is given and we need to analyze the amplifier. Okay. We need to determine its small signal voltage gain, small V 0 by small V I. Okay. This is a small signal voltage gain, and it is instructed to assume beta is equal to 100. Okay. So, now you see in this path VBB is given 3 voltage, right. So, if 3 voltage is given and this resistance value is also given, then we can start from here, right. Why? Because emitter is grounded. So, what we will consider the base voltage is, base emitter voltage is 0.7, right. So, this voltage is 3 volt, this voltage we will consider 0.7 volt. So, what we will get? We will get IB. Beta is given, from IB we will get IC. If we get IC, then we can get VC. Okay. Now, you see VC is plus 3.1 volt and VB is 0.7 volt. So, obviously, this is above 0.7 volt. So, this collector and base junction is reverse biased and base and emitter junction is forward biased, right. So, this is indeed in active region. So, next what we will do, when we are confirmed that okay, this is in operating in active region, then we will try to figure out the small signal gain. Okay. To do that, we need to find out certain values, right. What are the values? GM. GM is equal to IC by VT. So, IC already we have calculated, so we can calculate GM. Okay. Next is RE. RE is equal to VT by IE. Okay. And what is R pi? Beta by GM. So, if we have all of these, we will get R pi, we will get GM, and as early voltage is not given, we will not consider R naught. Okay. Early voltage is not specified. So, we are assuming there is no R naught. Then what is your gain? Minus GMRC. Okay. So, what we are doing? Up to this it is normal DC operation. Then what we are doing? We are considering all the DC sources, this 3 volt is grounded, this VCC is grounded, and we are adding only the small signal AC source. Okay. Then what we are doing? We are replacing this BJT by its 2 port network, small signal pi, hybrid pi network. Then what is this path? This resistance and this resistance. And what is this path? This current flowing through this resistance. So, what are the steps? First you do solve the DC equation, find out all the DC branch current, affirm that it is in active mode, and then you find out all the parameters that it will be required in the calculation of the small signal model. Then what you will do? All the DC sources you sort it to ground, then you replace this BJT with its small signal model. So, 4 step, actually 3 steps: DC, then equivalent AC circuit, and then equivalent hybrid pi network. So, your output voltage is minus GMRC into VBE, and then to get the voltage AV is equal to V 0 by Vi. Now, this is your complete circuit with all the coupling capacitor. Okay. So, ideally these capacitor values it should be large at the signal frequency. So, that signal frequency is behaving, the capacitor is behaving like a short circuit. Okay. The capacitor should be chosen like a large value, so that it is behaving like a open circuit at DC and behaving like a short at the AC. AC means there will be certain frequency, at that frequency it should behave like a short. Okay. So, such a way you should choose your capacitor. What is the impedance? 1 by j omega c. So, from the omega you should choose the value of c, okay, and omega is your AC signal frequency. So, if there is any DC source, we will consider that during the AC operation this DC current source is removed and it is sorted through the coupling capacitor, bypass capacitor, right. So, this 1 and 2 they are our coupling capacitor, and this 3 is our bypass capacitor. Okay. Now, this is our 3 basic configuration. Can you tell me this is real circuit or anything else? This is the complete circuit or something else? This is AC equivalent circuit. This is not the complete circuit, this is AC equivalent circuit. Okay. So, this is our common emitter. You see, emitter is grounded, input is given to base. So, emitter is common to the input side, emitter is also common to the output side. So, in common emitter, from where you are taking the output? Output you are taking from collector, input you are given to base. In common base, base is common. So, base is common to the input side. So, input is given to the emitter, right. Base should be common to the output. So, output is taken from collector. So, you see both of these cases output is taken from collector. Only what is the difference? In common emitter, input you are giving to the base, and what is base current? Smallest, right. So, you get a amplification IC is equal to beta IB. This, because of this your IB current will vary, and because of this variation you will get a bigger IC current variation, right, and because of this bigger variation you will get a variation in the V0 minus ICRC, right. So, it was in opposite phase. Now, see, in this case can you guess that it should be opposite phase or in phase? See, now base emitter voltage is base voltage minus of Vi, one minus sign already came, this minus sign will cancel. So, it will be in phase. Are you getting? If Vi is increasing, this V0 supposed to be decrease, but this is already in the emitter side. So, Vb, what is Vb? So, this will take care of this opposite direction of current flow. So, in this case it will be in phase, this is out of phase. Any other thing can you conclude? How should be the gain, large or small? Why? Emitter current and collector current almost same, right, and you see, okay, we will come to this later. Now, let us come to common collector. Collector is common. So, you cannot, in this case output was taken from collector, but now collector is common means AC ground. So, output should be taken from emitter. So, this is common to the input. So, input is given to the again base, and output we are taking from the emitter. So, this is common collector. So, this is our 3 different basic configurations. First one is common emitter, common base and common collector. Now, you see this is in direction of the current. So, voltage is equal to I into R. So, this is also positive. Okay. So, we will be seeing what is the relationship between their gain in these 3 configurations and what should be the application of these 3 different configurations, that we will discuss shortly. So, this is that we did in the first chapter, right. That is a model or symbol of a amplifier. This is a 2-port network and this how we figure out the output impedance. Okay. So, all of this amplifier you can make a symbol like this, or you can replace this with a 2-port network like this. Okay. So, if any input signal source is connected, if any input resistance is connected, then we will just, rather than drawing the amplifier, we can also draw the 2-port network and solve the problem. Okay. So, what is the relationship between Vi and Vsig? Vi is equal to just potential divider Rin by total resistance Rin plus Rsig into Vsig. This is my first part. What is the relationship between V0? V0 is equal to RL into current flowing, right. What is the current flowing? This current is flowing and this is the voltage drop and this is the total resistance. Okay. So, RL into AV Vi by RL plus R0. Then what is the gain in terms of Vi? AV0 into RL by RL plus R0. Now, if you replace this with Vsig, then this term will come, right. If you replace this Vi with Vsig, then you have to consider this is V0 by V0 is equal to a function of Vi. Now, if you want to make V0 as a function of Vsig, you need to replace Vi by Vsig. Okay, that is it. So, this is called the overall gain. This is our internal gain, right, only internal. This is internal gain, this is from source to output, and this is internal voltage, that is Vi, that is generated across R pi to gain. Okay. But you see all of these are the complex equation, they are just simple KVL or KCL. Okay. So, none of this is, all is just like a potential divider. This voltage drop is equal to I into R, and what is I? This V by this plus this, is not it? I is equal to V by total resistance. So, what it becomes? VDD into R2 by R1 plus R2. This is used everywhere, you see. Now, we can solve this small signal gain without drawing the small signal equivalent model. On this circuit itself, we can also solve this. Okay. If you, when you will be understanding this, when you will gain confidence, then rather than drawing the equivalent circuit, you can directly solve this on the circuit by considering this is performing AC analysis on the circuit directly. So, what is the actual circuit? Actual circuit is like this, right. This is your actual circuit. Now, what we will do when doing the performing the AC analysis? We will consider that this is grounded. So, we will just redraw this, this RC we will redraw, and we will consider between collector and emitter there is a resistance, that is R naught. What is this value of R naught? Early voltage by IC. So, this is our R naught. Okay. So, that we will draw. Now, you see this node is also grounded, this node is also grounded. So, they comes in parallel, and how much current is flowing through them in combination, that is minus IC. So, V 0 is equal to minus IC into RC parallel R naught. Okay. If you want to find out that what is IC in terms of this, what we will consider, that between base and emitter there is a resistance R pi. What is the value of R pi? Beta by Gm. This is just drawn here. So, why we are discussing this again and again? Maybe this circuit be a part of a bigger circuit. Okay. Then you have to analyze step by step, and once you are confident, you know, understand that what is the procedure, then you can quickly analyze the circuit without drawing the small signal model. Yes, you can draw the small signal model and solve the problem, but suppose you are in a hurry. So, on the circuit itself you can also calculate. Okay. So, these are few of the characteristics of the common emitter amplifier. What is our input impedance? This is moderate to low. What is input impedance? If you look in from the input side, what is your input side? Base. If you look from the base, what you see? Which resistance do you see? R pi. You see this. And what is R pi? R pi is moderate to high, right, because IB is very small. So, R pi is the value ranges from moderate value, moderate resistance to very high resistance. If you look in from the emitter, what should be your resistance? High or low? No, emitter current is high. So, resistance should be low. If you look from the collector terminal, what you see? R naught. Clear? So, you should be familiar with this. What is the looking in resistance? From the base, if you see, this is R pi, right. So, this is our input impedance. So, what is our input impedance? Moderate to low. And what is R out? Moderate to high. Generally, R out is very high, right. This R naught is generally, it can go up to infinity, right. And gain is high, and another is phase is, this is inverted. So, these are the main characteristics of common emitter amplifier. So, it can be used amplification, right. Okay. So, if you need, suppose in your signal chain you need an amplifier, then you can use common emitter amplifier. Now, suppose you have this circuit and you have this circuit. Additional RE is given. We discussed this, right. What is the job of RE? The job of RE is to provide you a negative feedback, so that you can overcome the thermal runaway, right. Now, what will happen to the gain? Let us calculate this. Okay. So, with this circuit we have find out that our gain is minus Gm RC parallel R naught, right, or say if we neglect R naught for the moment, let us say this is minus Gm RC, AV is equal to minus Gm RC without using the RE. Now, when we have a RE, something will change, right. So, you see this is our output. So, output voltage is again our V 0 is equal to again minus I C R C. This is same, right, because we are neglecting R naught at this moment, and output side there is only R C. So, again output voltage is equal to minus I C R C. This remains same. Now, what will vary? Vary will I C. Why? Because their previous cases all VBA was coming across this, now VB is subtracted because of RE, right. So, VB is little bit less because of the RE. So, IC will get modified from the previous circuit. So, we have to find out what is IC. So, let us find out what is IE first. Okay. So, this network is called small signal T diagram. Okay. As we have hybrid pi network, so this is T network. This is also equivalent hybrid pi model. Hybrid pi model can be redrawn like this. It is drawn based on the KCL. You see, this is our base current, this is our collector current, and this is our emitter current. So, this is drawn based on the KCL only. So, IE is equal to IB plus IC, that is it. Okay. So, it is drawn like this. So, I am having IC, I am having IB, and total KCL is IE, clear. So, I will write this IC in terms of alpha, alpha IE. So, IC is equal to alpha IE. And what is the looking in resistance in the emitter terminal? That is small RE, right. What we discussed, that small RE should be less than R pi, right. So, if you know R pi, so this is divided by, that we discussed in last class, because emitter current is beta plus 1 times IB. So, emitter resistance should be beta plus 1 times less than R pi, simple logic. So, what is the total circuit? RE plus capital RE. Okay. So, you see this T network is simple. What we are doing? We are drawing this in terms of emitter current. So, base current is coming directly, emitter current is coming alpha IE, and in the emitter side there is a resistance, that is RE. Okay. So, if I am giving a voltage of Vi, if I am giving a voltage of Vi and there is a resistance of RE plus capital RE, what is the current flowing through this? IE is equal to voltage by total resistance. So, Vi by total resistance is RE plus capital RE, simple. Okay. So, why we are doing this? We can do this with this hybrid pi model also. I can solve you, I will solve it with using this hybrid pi model, and you will see that everything will come same. Okay. So, let us see another approach. Okay. So, this is our voltage base to emitter. What is the voltage? Vi. So, what is the emitter current? Vi by RE plus capital RE. Okay. Now, see, if you look from this base terminal, because base current is less, right. So, base, if you look from the base terminal, resistance should be higher. Resistance should be higher by how much times? Beta plus 1 times. So, whatever the emitter resistance, what is the relationship between emitter resistance and base resistance? Base resistance is beta plus 1 times. So, emitter resistance is RE plus capital RE. So, if you look from the base, you will see beta plus 1 into RE plus RE, because base current is less, base current IB is much less. If IB is much less, the resistance in the base side, that should be much higher. What is the relationship? Beta plus 1. So, emitter side, if I look, what I am seeing? RE plus small RE. So, that will be multiplied by beta plus 1. So, if you look from the base side, you are seeing actually beta plus 1 times RE plus RE. So, what is the resistance ratio? If you have RE, when you are having RE, and if you want to see the RE when you do not have RE, clear. So, if you do not have RE, this is beta plus 1 times RE, R pi is equal to beta plus 1 RE, and if you have RE, then it is beta plus 1 times RE plus extra resistance this. Okay. If you divide them, what you get? 1 plus RE by small RE. Now, you recall what is small RE? Roughly alpha by GM. Okay. Beta is R pi is equal to what? Beta by GM. So, it will come as roughly come as 1 by alpha is nearly 1, na? Alpha is equal to 0.99. So, if you replace this RE by 1 by GM, it becomes 1 plus GM RE. What is the meaning? You see that if there was no resistance, and now if I put a resistance, my looking in resistance is getting increased by 1 plus GM RE. So, this resistance is offering me more input impedance, right. If this RE was not there, if RE is not there, what you see, that is R pi. What is R pi? Beta times, roughly beta times RE. Now, if you put this RE, now what you see? 1 plus GM RE. You will be seeing this resistance extra, this times. Okay. Getting my point? So, we get the I is equal to Vi by RE plus capital RE. So, let us calculate the V0. V0 is equal to IC RC, V0 is equal to minus IC RC is equal to minus alpha I RC. Put the value of I minus alpha I is equal to Vi by RE plus RE. Okay. So, what is your gain? AV is equal to V0 by Vi, this you see, this I we will replace with this, right, and what is RE? RE is equal to roughly alpha by GM. So, you see, if we take common minus alpha by RE, if we get RE, so it becomes RC by 1 plus, right, same circuit, I have just taken common this RE. Okay. So, you see, what is this alpha by RE? GM, na? RE is equal to alpha by GM. So, this term is minus GM RC, this term is equal to GM, right, and 1 by RE roughly equal to, if we neglect alpha, it is roughly equal to RE is equal to 1 by GM. So, 1 by RE is roughly GM, roughly if we neglect the alpha, so it becomes 1 plus. Okay. So, when we did not have RE, without RE, what was our gain? GM RC. Now, we have a RE. What is our gain? Increased or decreased? How much times? GM RE times. So, the times my input impedance increased, my gain decreased by the same ratio. You see, my input impedance was increased by 1 plus GM RE times. That means that we already know that negative feedback increases gain, reduces gain, right. If you use negative feedback, gain is reduced, input impedance is increased. By the same amount gain is reduced, the input impedance is increased by the same amount, and what is the amount? 1 plus GMRE. So, we solved this right in last class, that if we have a emitter resistance, we discussed that it is acting like a negative feedback and reducing our gain. So, that we solved today, and we figured out yes, it truly reduces the gain, because without this our gain was minus GMRC, and with this our gain is reduced by 1 plus GMRE times. Okay. But the advantage, our input impedance is increasing, that is good. Okay. And now you see, if you roughly neglect this one, so it becomes roughly GMRC by GMRE, GM get cancelled. So, it is a ratio of resistance. If it is a ratio of resistance, it is independent of the beta fluctuation, right. If beta fluctuate previous case, your GM will also fluctuate, beta is equal to GM R pi. If your beta is fluctuating, GM will also fluctuate. If your GM is fluctuating, your gain will fluctuate. Suppose you want to design a common emitter amplifier with a gain of minus 5. Now, temperature is changing. So, your minus 5 will always change, right. Sometimes it will be 5.5, sometimes it will be 4.5, you have no control. But if you have a gain which is a ratio of resistance, then if this resistance is increasing, maybe this resistance will also increase, but their ratio will remain constant. So, now you have a very tight control. So, your dependency on the beta is decreasing. Previous circuit you do not have any control on beta, right. But using this circuit, using just a small resistance at the emitter terminal, now you see your resistance is, your gain is independent of beta variation. Okay. So, your gain is reduced by a term, so 1 plus GMRE, and by the same term your input impedance is increased, your overall voltage gain is less dependent on the value of beta, and high frequency response is improved. So, these are the advantage of using the negative feedback. So, what we arrived, that with this our AV is equal to minus GM RC with emitter resistance AV is equal to, that gain is reduced by the 1 plus GM RE times. Okay. So, the emitter resistance is actually decreasing your gain. So, that is why sometimes it is called degeneration resistance. Okay. Regeneration means to increase, degeneration means to decrease. So, this is the complete discrete common emitter amplifier. Discrete means on the board, when you will be doing the lab experiment in the analog electronics laboratory, some IC for this BJT will given, discrete IC, discrete IC for the BJT with others discrete component. Discrete components like resistances, capacitances. So, this is all the component are separate and you are putting them together in a, are you doing the lab? In the breadboard, right. So, that is why it is called discrete, but if you have a complete IC, then all of this will be integrated. Okay. So, there is a difference between the VLSI circuit and the discrete circuits. So, discrete circuit we can use bigger values of capacitor, because capacitor value we are putting on board. So, area size is does not matter that much, we have enough area. But when you want to design an integrated circuit using a VLSI design, then area is important, right, because for more area you have to pay more. Then what you will try to do? You will try to reduce area as much as possible. So, all of these coupling capacitor you may not use in the case of integrated circuit design, because there is require large value of capacitor. Okay. So, discrete biasing is little bit different than integrated circuit biasing. So, we may not use large value of capacitor because of the area constraint, because in this we have a constraint on area, we want to reduce it as much as possible. So, if this is your equivalent circuit, to draw the small signal model, what you will do? You will consider that all the capacitor are shorted. Okay. So, this is redrawn here by considering VCC is shorted to ground, all the capacitor are shorted, and this will look like this. Okay, that we have discussed several times. Why we are discussing several times? So that you get familiar. Okay. And if early voltage is considered, another extra term will come, that is R naught. Now, this is biasing. This biasing already we know. What is this? Potential divider biasing. Okay. So, this is our actual circuit and this is our equivalent circuit. What is RBB? R1 parallel R2. And what is VBB? This is V Thevenin, this is also R Thevenin, right. So, V Thevenin is equal to R2 by R1 plus R2 into this. So, this is different biasing technique, means we will design the circuit such a way so that our this voltage is arrived. Okay, this is one technique. There are other technique also. Let us see those. This is another technique. This is known as 2 power supply biasing. You see, now there is no VBB, but still will it work or not? It will work, because this terminal is negative. If this terminal was grounded, it will not work. But I have a 2 power supply, one is positive, another is negative. So, this will also work. Okay. So, this is known as the 2 power supply biasing. If I have a 2 power supply, I do not need a generate VBB, directly use the RBB and you are done. So, this is our second technique of biasing. Third, collector to base feedback. This collector potential, I am taking a part of it and putting it in the base to generate the VBE. Okay. Some base current will flow through this, IBRB drop, that voltage will come to provide our VBB or VBE. Okay. We need roughly 0.7 volt. So, if drop is roughly 0.7 volt, we are through. So, we will choose the resistance RB such a way, so that at least 0.7 volt is generated there. So, this is our third technique. Fourth technique is using a current source. So, this kind of biasing we will be seeing in differential amplifier. Okay. And this is known as the current mirror. What is the meaning? You see, if IRF current is flowing through this and it see base and collector is shorted, base and collector is shorted means base potential is equal to collector potential. So, whatever is the C, E and E, that is the V, B and E. So, its base and its base are shorted and emitter is grounded. So, their base emitter potential is same, na? VB1 is equal to VB2 and collector current IC is a function of VBE. So, if their base emitter voltage are same, I can tell IC1 is equal to IC2. In IC1 what current is flowing? IREF. So, IC2 will be also same. So, what they are doing? They are mirroring the current. This branch, this current, it is a mirror image of this current. Clear? So, this configuration is known as the current mirror. Will be exactly same? No, little bit different will be there. Because of what, can you tell me? Because of early effect. If it is a early effect, then IC depends on, IC becomes a function of, now its collector potential and its collector potential, they are different, right. So, if your current is constant, then you are done, they will be same, but if your collector is varying with VCE, then what will happen? If this collector potential is changing, so this current will little bit vary with this, but small variation. Still you can assume, you can neglect this early effect and assume that these two current are same. There are some assumption, we are neglecting IB, okay. Otherwise you have to subtract IB and then you have to. So, this small assumption we are considering and we can assume that okay, this is this, otherwise we have to subtract the base current from this and it will be. So, this is a approximation, consider IB is equal to close to 0, neglecting IB. If you want to calculate the real, then you have to do the KCL and IREF is equal to IC plus 2 IB, right, this IB plus this IB, then you have to subtract this, then you will get the actual relationship. But roughly you can assume that okay, there is no early effect, there is base current is 0 and then truly a mirror. Okay. So, this mirror or this current source, they are also used for biasing. So, this is called constant current source biasing. So, how many we have learned? Constant current source biasing, collected to base feedback resistance biasing, to power supply biasing, potential divider biasing. Few other techniques are there, but these are most important. So, let us stop us today here and we will continue from this in next class.